I'm not going to do all the details of the proof, but as I said in office hours, the change of variables theorem is one of the big theorems in mathematics that everybody uses, and it's actually going to be crucial for us to understand how to do integrals of things on manifolds coming up soon. But if you actually poll most people that have PhDs in mathematics, very few of them actually have been through a proof of this theorem. When you get to 8,000 level real analysis, you learn a more powerful notion of integration called Lebesgue integration. And using Lebesgue integrals, the proof of this theorem becomes easier. But even so, most graduate courses don't bother taking the time to explicitly do it. So I want you to have some idea of why the theorem works. I'm not going to do all the details. I'm not going to hold you responsible for any of the details, other than the first thing we're about to do, which is something we're going to use all over the place in chapter 6. So I remind you that the theorem says the following. Suppose, so we have this picture, right, where we have our change of variables function g. You've got some region, omega in U space, and it's mapping to some region we're calling S in X space. And we have the supposition that G is mapping some open set in Rn C1, and it's a one-to-one function. And we said, suppose omega is contained in U, and F is mapping G of omega to R is integrable. So F is a function here. And we're trying to integrate F over this region S. So the integral of F, and I'll emphasize the variables here. So this is supposed to remind you of change of variables you did in Calc 2. It is going to be rewritten as an integral back on omega by putting in the composition of functions. So you're going to write x equals g of u. That makes sense. Just like we did in your substitutions back in single variable calculus. But then remember, when you made your substitution in single variable calculus, you had to have a g prime of u here. When you put x equals g of u, dx became g prime of u du. I hope everybody remembers doing that. Well, that gets replaced here by the fudge factor, which is the absolute value of the determinant. Is that right? And I'm going to say, then this is true, provided we assume the right-hand integral exists. In other words, I'm going to assume the function phi given by fog times the fudge factor is integrable. All right, so that's the statement. And again, I remind you that this should remind you of just substitutions, where you say integrating f of x dx is the same as integrating, making a substitution back when you did Calc 2 integrals. You let x equal g of u, dx becomes g prime of u du formally. U went from a to b, and x goes from g of a to g of b. So this should look exactly the same, except for one thing. What's the one thing that looks different?
It's not absolute value
I have an absolute value here, and when you learned substitutions in Calc 2, you did not put absolute value in. What's wrong? Suppose G prime were negative. Why is this still correct?
That's sign.
G of A.
Hmm?
It has to. So G of B is going to be like. That'll also be negative. G of A will be negative.
No,
Well,
but
not
you're on the
negative-
right track.
Not negative, but
G
sign
will be
negative.
less.
If that makes
If
sense.
G prime is negative, that means G is decreasing. So as you go from A to B, what does G do? It goes down. So you're going from a larger number to a smaller number.
So it's going to be negative as well.
So the convention is the way you do that is you switch, right? Here, when we're doing absolute values, we're talking about integrating over a region here and a region here. We're not talking about turning the region upside down. So when you go from, if you were going to say integrate over G of this interval, that would be this interval, and you would normally write it from here to here when you did the interval. So that minus sign in the sign of the derivative is being absorbed into making those go the usual way.
Well, what if it's only negative on just a part of
It's supposed
the
to-
interval?
So when you do substitutions, you're not supposed to allow the function to turn around. In principle, it's supposed to be a one-to-one substitution.
Okay,
In
right.
single variable, it doesn't hurt you if it isn't. In multivariable, it will.
Okay, that
So I'm
makes
putting
sense.
this hypothesis in here.
So you may have just answered this question explicitly, but so will this theorem does that allow for use of substitution?
Mm-hmm.
And so without it, we could.
I mean, I'm saying you can deduce this
From-
as a special case of this, although it's really silly, because this is a one-line proof in calculus. All right, so what I want to do today is sketch the ideas of the proof. We're not going to come anywhere close to doing them all. The main tool we're going to use to understand things getting off the ground, and we're going to use this throughout Chapter 6 as well, so I might as well just do it. Is something called the mean value theorem. Ever heard of that? Now I'm going to change its name and call it the mean value inequality. Because that's what it really is. So here's the multivariable version of the mean value theorem. Suppose f is a vector function now that maps some open set in Rn to Rm. They don't need to be the same. And suppose f is C1. For purposes of what I'm going to state and what we're going to use, I'm going to say suppose U is convex, although we don't need that. So what I mean by convex is that if 2 points are in there, the line segment joining them is in there. So if A and B are in U, the line segment joining them.
So that's different than our idea of convex from like second derivatives.
Right.
Okay, it's
Is this similar to that homework question?
The homework question you were thinking of was assuming connected,
Right.
that there was a path, and in fact, what I'm going to state here would work just with that.
Of where's the line segment? So
But I'm actually going to state line segment just because that's all we care about, and it will make the proof a little bit easier, not much. So here's the statement. You want to estimate how much f changes when you compare it at A and at B. So this line segment joining A and B maps to some curve that joins f of A and f of B. And I want to estimate how far away from f of a could f of b be? So the usual mean value theorem that you remember from calculus and that we did last semester in review said the distance you travel between time A and time B is was exactly equal to your speed at some time in your trip times the time change. What I'm going to do here is not try to say what it equals, but what's the biggest it could be. And the mean value inequality says something that's reasonably obvious. If you take the maximum of the norm of the derivative, remember the norm of a matrix tells you how much the matrix stretches things. So the maximum norm of the derivative in the interval from A to B, in the line segment, you take all the possible x's that are in there, and you say what's the biggest the derivative ever is, that tells you that that number times the distance between A and B gives you an upper bound on how much f can change.
Sorry, was norm the max that
This
max
is the matrix norm.
Yeah, the matrix norm. It was going back to just
It was the maximum amount it stretched unit vectors.
okay.
Okay. So I think I will actually save the proof for next week, just because if I do the 5 minutes now, I'm going to run out of time.
Is that x an interval notation?
By this I mean the line segment joining A and B. So take all the x's in the line segment between A and B, and take the biggest. So the proof of this, which I will do next week, is just the fundamental theorem of calculus. It's really very easy. So proof next week just uses the fundamental theorem of calculus. But I want you to realize that if we're interested, I'm not going to apply this to the f in this problem, I'm going to apply it to the g, so I should have stated it with g. But I'm really interested in saying, if I have 2 points that are reasonably close here, how far apart can they be here? How much can g distort distance? Okay?
What's that max thing? Maximum of what?
Of this.
Isn't norm already max?
Yes.
But it's for different.
But I'm taking over for all the x's. So, yes, the norm of a fixed matrix is a max, but then I'm saying do it for all the x's in the line segment. So this is the maximum amount f, the derivative of f is stretching it along any point on that. All right, so here's going to be the key idea. No, it's still wrong. Erase that from the tape. Doug is hacking us with incorrect differential geometry. So the application of this, of the mean value theorem, is to prove the following.
Like mean value inequality theorem?
Yes.
Okay.
So this looks somewhat technical, but I want to ask you the following question. So, suppose, how specific do I want to make this? Suppose phi is a map from an open set in Rn to Rn. So this is the same dimension now. And I'm going to suppose U contains a ball of radius r. Centered at the origin. Suppose phi is C1, the origin is in U, and the ball of radius r, centered at the origin, closed ball, is contained in U.
Did you have to write 0 is element of u when saying the ball?
Yeah, I'm just specifying.
Okay, speaking.
So here's what I want to say. I'm interested in knowing how much, when you map by phi, how much does this ball distort? Well, suppose phi were the identity function.
Not at all.
It wouldn't distort at all. So let's suppose that for x in this ball, that the derivative of phi at x is very close to being the identity matrix. So the best linear approximation of phi is very close to the identity. What does that tell you intuitively? So phi maps 0 to somewhere. What do you think is true if phi is very close to being the identity?
Doesn't change the area very much.
Then it's going to map 0 somewhere, but it's not going to distort lengths very much from, so the ball won't go to a ball anymore. It'll go to some shape. But it can't be too much distorted from the original ball. And here's what I'm actually going to say. The dilemma says you can fit phi of the ball inside a ball of slightly larger radius, centered at phi of 0. And the most the radius can expand is 1 plus epsilon, or this is the epsilon. And you can't lose too much either. It actually has to contain a ball centered at the point, want to guess, of what radius? Yep, 1 minus epsilon. So if it were the identity on the nose, it would just map to a ball of radius r. But if the derivative is very close to the identity, that epsilon is telling you that you have to actually trap a ball of slightly smaller radius and be trapped inside a ball of slightly larger radius. So that's the statement of dilemma. Then phi of the ball of radius r is contained in a ball of radius 1 plus r epsilon, and it contains a ball centered at phi of 0, radius 1 minus epsilon r.
Should I just close ball for you up? X is an element of the up one line. Suppose for, should that be a closed ball or no?
Doesn't matter.
Should it be on the bottom right, 1 plus
1 plus epsilon
times
r.
Yes. So why do we care about something like this? Well, if you think about integrals, we're going to have to chop things into little pieces, and we're going to have to control how the little pieces are mapping. And so we're going to be able to say that if we have control on the derivative of phi, then we're going to be able to apply this lemma and say something about how balls or little cubes are distorted. So here's the setup. We'll see how far I get in terms of time. So let's do a sketch. So your favorite homework problem from the first assignment is about to show up. Well, it should be. So the usual game is going to be, look, we've got this region omega that's inside this open set on which f is C1. Then I can cover omega with rectangles that are all contained inside of U, etc. So cover omega with rectangles, all contained in U. And basically, we're going to reduce to the case of a single rectangle. So I'm going to end up proving the theorem assuming that my function is just on a rectangle. And in fact, I'm going to even cut it up into cubes and just do cubes.
Why do you need that to make it like isn't you? They are two.
Omega, remember, is a region,
Or you
which
is-
means it's compact,
you is-
and U is open. So that means you can always fit little open sets around omega, and then these rectangles will be contained in those, yeah. All right, so I'm going to cover with rectangles, and I'm going to do the proof for just a single rectangle. Now, you're going to complain to me that if I'm doing the integral of f, what do I do if I'm working on a rectangle that looks like that?
Give the outside zero.
We do our f-twiddle thing where we make, or whatever we called it, where we make f be f here and 0 outside.
We use Russell.
No, we did not. No. All right, so now assume f is bounded. Well, that's no assumption. Because when we talk about integrable, there's always bounded functions. Now here's going to be a weird assumption. I'm going to assume that if I take the derivative of g at points of omega, that the inverse matrix of that has bounded norm, given by some bound n. So I'm going to have, basically, because I have continuous functions on a compact set, I have maxima for things. So I'm just going to assume there are these numbers that are going to come into the proof somewhere. Okay. Here we go. We're going to try to now choose some size of cubes so we're going to try to dissect our region R, our rectangle R now, into little cubes. And I want to control a bunch of things with the size of my cubes. All right, the first ingredient is your favorite problem from section 1.
Are cubes just like rectangles?
But I actually mean cubes. Same sizes.
Oh,
Because,
okay. Right.
well, okay, I already told you this is full of technicalities. All right. First thing you know from homework, there is a number delta 1. There's going to be a bunch of deltas coming here. So that whenever the diameter of our cubes is less than delta 1 in this case, we have upper sum minus lower sum less than epsilon. So, of course, at the very beginning I should have said choose epsilon greater than 0. Right. Should have said that. And we're going to end up with epsilons flying around that we're trying to estimate things by. Where did this come from?
It was that homework problem with the bad partition and good partition.
Right. This was the problem you guys all did where you considered good and bad rectangles that proved that because of the convenient criterion you could prove that there had to be a delta. If you took any partition where the size of the rectangles was less than that delta, upper sum minus lower sum, is always going to be less than epsilon. All right, so that's my first step. Here's my next one. Ah, but I just already screwed up. I already screwed up because f has no business being on my rectangle back here. It isn't f. Who is it?
G.
But what am I actually trying to integrate?
E.
Over omega, what am I trying to integrate? That horrible
V?
mess. which we called phi.
Wait, squirrely phi or like straight phi?
What?
Isn't that
Yeah,
also?
there's two
Oh.
different fees on the board.
Curly phi. I'm all right. I'm all right. I just didn't even think about how I was using two different phis. The phi is the function that we're integrating here. And that's the integral I'm doing over omega.
So phi is fog. So we think of it as like fog.
It's fog together with fudge factor. So if I'm talking about partitioning R here, it's inside omega, and the thing I'm supposed to integrate over that is that function phi. I'm going to end up relating that to how you integrate f over s in a minute. Okay. That's step one.
E is found.
No. I mean, it's true, but I'm going to care about f here. All right. Next. By uniform continuity, of G, we have whenever x and y are less than some number delta 2 apart, which one do I want to do first? The derivative of G at x minus the derivative of G at y, norm. So again, that's that same norm of a matrix stuff. It's going to come out all over here. This is going to be less than epsilon over n when x minus y is less than delta 1, delta 2. No, I already said whenever. Okay. So I'm controlling how close points have to be to make the derivative of G not very much.
And is that because we know the derivative matrix is continuous?
Yes. So G and dg here, right? So G is C1, that means the derivative is continuous.
Mm-hmm.
So by uniform continuity, I'm applying
And we
this.
know that the inverse of the derivative is a variable matrix because it's 1-to-1.
Well, correct. But I should have actually stipulated that some, yes, there.
Because that makes a non-singular.
I actually want to make sure that dg is everywhere non-singular. So I'm actually making a stronger assumption here than I put in the hypotheses. Still correct to state it, but I'm assuming a little more than proof. Good. All right, now there's another crazy one. Whenever x minus y is less than delta 3, I'm going to have that the determinant of dg at x minus the determinant of dg at y is less than epsilon over m. All right, so I've put all these deltas into one magic bag, and I shake them up. And now we're going to work with, right, we're going to work with a delta that's less than or equal to the minimum of all of those. So whenever I need some hypothesis, I make sure my delta is small enough. All right, now here comes the idea. I've got my rectangle, which, so I didn't assign the problem to everybody. It was a challenge problem. You might have to fiddle with the rectangle slightly so that you can divide it into cubes. So you need the size of the rectangle to be rationally related. So you might have to stretch the rectangle slightly. We're going to divide the rectangle into cubes. I'm not going to draw them all because I'm already tired. Okay, I've drawn them all. Those are all cubes. And I'm going to just say each of these cubes is an R sub I that's centered at a point A sub I. So that's a blow-up picture there of that little cube. And what I want to do, as we've done before, when we did, for example, the proof of Fubini's theorem, is I want to think about adding up what happens on each of those little pieces. So, let's take the integral of f over what g does to that rectangle. So this is my rectangle R that I drew there, that I've divided into these little cubes. This is R, and I've written it as a union of all these cubes, R sub I. And I'm going to say, what's the integral of f over g of that? Well, it's the sum of the integral of f over all the little subcubes mapped over. You can't argue with that. Now, let's think about what we can say about the integral of f over over the image of one of those subcubes. Well, this isn't a cube. This isn't a rectangle. It's some weird thing. It's a region. But what do I know from homework you've done and from common sense? What you know is that the most this could be is the sup of f on that times the volume of that little piece. And you can start to feel, when I start writing that down, this stuff is going to come into play. That we're going to use the estimate on derivative to estimate how much volume there can be in that thing. And what's the smallest it could be? Well, little mi, the nth, times volume of g of Ri. Where what? Little mi and big Mi are respectively nth and the sup of what? F on this. So that is the nth of the sup of fog of x when x is in R sub I. Okay. Now, what do we know about the volume of g of R sub I? Well, okay, so there's a problem here. This assumed that my derivative of my phi was close to the identity.
And we had a circle.
Yeah, so
that's supposed to work for any shape.
it basically, the reason we want cubes is going to be that you can do the bookkeeping if you so desire and say, if I have a cube, I can put it inside a ball.
Okay.
And then what happens to the cube, and I can put a ball inside it that's a little smaller if I have to. And I can sandwich where the cube goes by saying that it contains wherever that ball maps and is contained in wherever the big ball maps. So I can reduce everything to this thing here. If you look in the book, I did something I skipped here because I was trying to make it simpler. Haha. So in the book, there's actually a notation for norms with a little cube underneath it, and I'm avoiding that. But if you read the book, you'll see that there.
It's actually a picture of a cube.
Hmm?
There's like a little figurine of a cube underneath the.
Yes. But I mean, the way I wrote the proof in the book, I based everything on working with norms built on cubes instead of spheres, instead of balls. But you don't have to. All right. So the claim is going to be that the volume of G of Ri can be approximated by saying, look at the center of the cube and think about balls centered at the center of the cube. Well, I'm going to have to use the derivative at the center of the ball to approximate the derivatives of the function at nearby points. So I'm going to use the derivative at AI, and I'm going to say, well, that distorts volume by a factor of absolute value of its determinant. Right? If you have a linear map, we know that it distorts volume by that fraction, or that amount. And then I'm going to say, by this lemma, where phi is being built out of comparing so I'm going to write this down, but you feel free to ignore it. So basically, I'm going to invert the derivative at the center of the cube and use that linear map times the actual mapping.
Which phi is that?
That's this phi. No, I have it right.
You had it right.
It's this phi, and what I've made it do now is I've made the derivative be close to the identity, because at AI, I've got the derivative of G at AI with an inverse out here, so that is the identity. And because G is C1, for nearby x's, the derivative will be very close to the identity. So you're going to use the lemma to deduce that if you distorted G by this linear map factor, then you would end up with this stuff here. And what I'm telling you is, and it's written out more carefully in the book, that what that tells you is that the volume of G of Ri is this distortion factor coming from approximating the function by the derivative at the center of the cube. And then you use the radius of the cube, basically, and say, I'm going to have an outer estimate and an inner estimate by multiplying by a factor of 1 plus epsilon to the nth times the volume of Ri. So that's coming from this and this. So.
Okay, so the volume G of Ri was not equal to just determinant of D. You were like adding stuff later.
And roughly speaking, we're saying if it were just a linear map, it would be the volume of your original region multiplied by the absolute value of the determinant of the derivative.
Oh, yeah.
But then I'm saying that lemma means I have to fudge and allow it to be inside a slightly bigger one and be containing a slightly smaller one.
I thought it was just equal to the determinant. But no.
If you had a linear map, but we don't. We're approximating G by a linear map on this little set.
Okay.
G is not linear. But if it were, this wouldn't be there.
Okay, but the volume of Ri would be there.
That, right.
Oh, okay, that, yeah.
Right, so this is allowing us to control for the fact that the map isn't linear, but we're controlling it because of this lemma that I'm not proving today.
Who's the nth vowel from?
In dimensions.
Because we're in n dimensions, so you're getting, if the ball stretches by that factor, its volume goes up by that to the nth. All right. We're more or less getting close to the
halfway point.
Now we're past the halfway point, which is good. All right. I need one more bit of notation now. So I now need to do mi's and big mi's with twiddles on them. Tildes, twiddles. This is going to be the nth, respectively, sup of other phi. Groups phi of u for u in Ri. Yeah, I should have had a u here too. Right, the x's are in the other space. Okay? So now what do I have? Well, then there's a little bit of something to check, which is again done in the book. And that is that if I take the sup of f composed with g, this guy, and I multiply it by the determinant of the derivative at the center of the cube, then surely that can't be too far off from looking at the sup of phi. What was phi? Oh, I erased it. Phi was right, it was fog times the absolute value of the derivative. So if I take the biggest that the function can be times the absolute value of the determinant at the center of the cube, that is roughly the maximum of little phi. But it might turn out that it's a little bigger, or it might turn out that it's a little smaller. Again, this is if the cubes are small enough. And similarly, the minimum times the absolute value of the derivative at the center is greater than or equal to the minimum minus epsilon, and twiddle of phi minus epsilon. All right, so where does this put us? Actually close to the end. I'm going to come back to this, and I'm going to plug in, and I'm going to say the integral of f over g of Ri is less than or equal, we said, to big Mi volume. Big Mi volume. Well, we said the volume was less than 1 plus epsilon to the nth times the volume of Ri, times the determinant, sorry. Plus epsilon to the nth volume of Ri. Okay, so I plugged in this. Now this looks like big Mi times determinant of derivative. What did we say about it? This is less than big Mi twiddle, give or take a little, times, well, more or less 1, but a little bigger, times volume of Ri. And similarly, you'd get something like that on the bottom here. So you'd have less than or greater than or equal to Mi twiddle minus epsilon 1 minus epsilon to the n by volume of Ri. So this is looking, morally speaking, if we now added these up, I would have the integral of f over g of r sandwiched between something that looks very upper summish and something that looks very lower summish. These guys look spiritually, although not precisely, They look like upper and lower sums for what? Yes, phi.
I just use probability, there's twice as many pieces in there.
Right. Those look like saying this looks like if I had the mi twiddles times the volume of Ri, that would look like an upper sum for phi.
Right.
But I don't have that. I've got epsilons messing with me.
He's multiplying
But it's
out.
less than.
But I've got some huge constant that will multiply how much epsilon can contribute. And on the lower side, I'll have something that looks like, oh, this is sum, sorry. That's what it is, right? On the lower side, I'll have something that looks like a lower sum minus some huge multiple of epsilon. And that looks like a lower sum. And then you say to yourself,
So,
if these epsilons weren't here, it would look very familiar. Well, hang on. What would we deduce? Knowing that phi is integrable, if we didn't have these epsilons, without the k epsilons, we deduce, because phi is integrable, that what is true.
But the middle thing's the integral of phi over r.
That if this is true, this must be very, very close to the integral of phi, because the integral of phi is the unique thing between all upper and lower sums. So we deduce that because epsilon can be made as small as we want, we would deduce that in fact the integral of f over g of r is the integral of phi over r.
So I'll just choose this one now, because we're leaving this one.
But the problem is that these epsilons are there. And so I'm not going to have the time to write out the argument, although it is in the book. What you need here is a fancy schmancy, if I can spell that, fancy schmancy
Yep.
version of the convenient criterion. You need a convenient criterion that basically allows you to be within epsilon of being sandwiched between upper and lower sums. So here is the version, basically. Suppose phi is integrable, and for each epsilon, we have a number I that's between the upper sum for phi plus epsilon and the lower sum for phi minus epsilon. We have partition P so that this is true. So then what you want to say is that I has to be the integral of phi. And it's true. Even if you allow yourself epsilon error between upper and lower sums, because you can make epsilon as small as you want, this number has to actually be the integral on the nose. Because if it weren't, if it differed from the integral by 0.03, by choosing epsilon small enough, you could contradict this if this were 0.03 off. So I was going to do the proof, but I'm out of time and you're glad I am. But you see, in summary, the strategy, it's a technical mess. And I didn't use everything I put on the board, but it all gets used somewhere in filling in details. The idea is chop into small pieces, see what happens on a small piece. You can sandwich what happens to a little cube between big cube and little cube of something you can control. And the big and little are really close. Therefore, in the limit, you get the right interval. It's a pain in the butt. But the key features are understanding, of course, that determinant comes in because that's telling you how volumes transform when you have linear maps. Approximate the function g by something linear on a small enough piece, and then you put it all together. Okay, have a good weekend.